All right, here we go. So this is going to be a video for section 8.5, trig form of a complex number. And I'm going to actually split up section 8.5 into probably 3 videos. We'll see how it goes, but that's my plan. So this first video is just to really talk about what is trig form. We're going to remind ourselves what a complex number is. Then we're going to talk about trig form and what that is, and then we're going to look at how to convert. So it may not make any sense in this video why we have trig form, but there's so many things we can do with trig form that are much easier when we have that. And you'll see those in the other videos. So first of all, let's remind ourselves what a complex number is. So remember we had imaginary numbers. So imaginary numbers, those are basically the things with an I in it. So, 3i, 7i, negative 10i, 1/2 I, even pi I. All those are imaginary numbers. And then real numbers are basically anything without an I in it. Anything that you can think of without an I, any kind of number. So negative 2.8, 17, pi, e, negative 20. Well, coming up with random numbers is hard. So anyway, those are all real numbers. What a complex number does is combines them. What if you want to combine a real and imaginary number? So a complex number would be things that look like this. 2 plus 3i. So it combines the real part. There's the real part, the 2, and then it combines the imaginary part, 3i, into one whole big number, and that's the complex number. So, whoops, let me go back to a pen. 7 minus 5i, 2 plus pi I. Those are all complex numbers. Now, it's a little weird because even something like 0 plus 3i is considered complex because 0 is a real number, 3i is an imaginary number, and we've combined the two of them together. So it's a complex number. But we also know when you add anything to 0, it stays the same. So this is the same thing as 3i, but wait a minute. 3i is imaginary, but it's equivalent to this, 0 plus 3i, which is complex. So wait, is 3i imaginary or complex? And the answer is yes. It's both. And we have some numbers that are both imaginary and complex. Also, real numbers can be considered real and complex. So for instance, I could have something like 5 plus 0i. Again, we've got the same kind of thing we had over there with the imaginary. 5 is real, 0i is imaginary. We can combine them together and we get a complex number. But this is equivalent to 5, so all real numbers are also complex. We can think of this as in a Venn diagram. So I'm just going to go ahead and, if you want, for fun, you could stop the video right now and think about how you could make a Venn diagram to represent the relationship between imaginary numbers, real numbers, and complex numbers. So if you want to go ahead and do that, go ahead and hit pause, see what you can come up with, but I'm going to go ahead and continue on with that idea right here. So if we take 2 circles and overlap them, the rectangle is going to represent complex numbers. One of the circles will represent real numbers. Another circle will be imaginary numbers. So, real numbers we know. I just listed a whole bunch up above, but anything without an I. 7, 12, negative 1, E. So all of those are real numbers, but you could also think of them as 7 plus 0i, 12 plus 0i, negative 1 plus 0i, e plus 0i. So that's why then these also belong in this big rectangle because they are also all complex. Sorry about my dog. You're going to probably hear a lot of them throughout these videos. Hang on, I'm going to just pause. Sorry about that. That was the mailman, in case you were curious. My dog has saved me from the mailman, as he does every single day. You'd think he would get used to it. Anyway, I think we were talking about real numbers and why they belong in the box of complex numbers, and that's because every real number is complex. And then likewise, every imaginary number is also complex, because things like 7i, negative 8i, 19i, and so on, all of those could be 0 plus 7i, negative, or 0 minus 8i, 0 plus 19i. And so they have a real and imaginary part. So all imaginary numbers are also complex. But notice that there is a place right here that is overlapped. So there is something that is real and imaginary, and it's also inside the box of complex numbers. So it's also complex. And that one special number, think about it. And again, if you want to pause the video to try to think about what number is real, imaginary, and complex, and the lucky winner is 0. So, and then we have numbers, like 3 minus 5i, 10 plus 2i, and so on and so on. And those numbers don't belong in the circles because they're not real or imaginary. They have a real part, and they have an imaginary part. But the number themselves, 10 plus 2i, is a complex number. So, a little bit about what a complex number is. Now, one thing I do want to, there's a standard form for complex numbers, and it's a plus bi. It's standard that we write the real number first and then the imaginary part. So, likewise, if you've got something like 7 plus 2i, so we've got the real part, then the imaginary part. If you had something like, let's say 8 minus 5i over 3, it's not really considered in standard form. You would have to write it as 8 thirds minus 5 thirds I. And then we can clearly see what the real and imaginary part is. I'm just going to go ahead and scroll it up. But the real part, because we talk about real part and imaginary part all the time. So the real part is 8 thirds. And then the imaginary part is negative 5 thirds I. So it's standard that we write them like that, where we'll actually have the A part, and then, ooh, sorry, my hands are so big. You have the real part, and then you have the imaginary part. So anyway, I just wanted to get that out of the way. Okay, so that's what a complex number is. Now let's look at absolute value is a good thing to know about complex numbers. Remember, in general, that absolute value is the distance from 0. In case you didn't know that, now you do. So we say that the absolute value of 5 is 5, because on a number line, 5 is 5 units away from 0. Likewise, negative 5 also has an absolute value of 5, because on a number line, negative 5 is also 5 units away from 0. How do we do that for a complex number, though? What does it even mean for a complex number? And so here's where I'm not sure if you saw the complex plane last year in Integrated 2. I don't believe you did, but in case you did, it's a good review. So let's scroll this up here. I'll leave that right there. We have the complex plane. And luckily, the complex plane, it works a lot like you would think. It's a plane. We already know about the coordinate plane, and it works a lot like that coordinate plane. You have two axes that are perpendicular to each other, kind of like the x and the y-axis, but it's not the x and the y-axis. one is the real axis and the other one is the imaginary axis. And then we can plot numbers. Instead of plotting a number on a number line, we plot complex numbers on a complex plane. Because remember, complex numbers have a real part and they also have an imaginary part. So you can't plot a complex number on a real number line or an imaginary number line. It's going to take both of them together. And so if I took this number right there, you guys are probably already thinking about it, what that would represent. That is 4 units on the real, 4 units on the real axis, and it's up 2 units on the imaginary, so we say it's positive 2i, so you put the real and the imaginary part together, and that point right there represents 4 plus 2i. Nice and simple. This number right here, think about what that would be. That would be negative 1 minus 1i. Or think about what this would be if I'm just right there on the imaginary axis. If you were thinking for I, you are correct. So now think about like where, let's just say, where would you put negative 5 plus I? And 1, 2, 3, 4, 5 plus I. If you were thinking right there, you were right. Over negative 5 on the real axis, I'll put positive I on the imaginary axis. So, and by the way, in case you were wondering if I was going to label the axis, this would be I, this would be 2I, 3I, and so on. And then you have the negatives down below, negative 1I, negative 2I. I just don't have a good place to put them. This would be 1, 2, 3, and so on. So that's the complex plane. So now if I want to do the absolute value of a complex number, then it's just a matter of the distance from 0. And 0 would be at the origin. So I'm going to go ahead and go to a new page to talk about this more, but you're probably already thinking about it. It's the Pythagorean Theorem. All right, so absolute value of a complex number. So we're going to let z, I don't know why, that's a funny looking z. Z is often used to represent a complex number. Doesn't have to be, but it's just often used. Kind of like x's are often a variable that represents some unknown. Anyway, we're going to let z equal a plus bi, then the absolute value of z equals, and if you want, go ahead and pause the video, see if you can predict what it's going to be. And now I'm going to go ahead and go through it. So again, going to this guy right here, where this is the real and this is the imaginary. You do need to label the axes as real and imaginary, because if you don't know it's not a coordinate plane. That's your way of saying it's a complex plane. So it's kind of standard that we label horizontal with real, vertical with imaginary. Boom, now we know we got a complex plane. But I'm just going to go ahead and put some random a plus bi right up there. I want to know what the distance from 0 is, so I want to know how long that is. But I can make a right triangle out of this. This leg is A, this leg is B. This would represent the absolute value of z, and so you can see that it's just the Pythagorean theorem. So it would be a squared plus b squared equals the absolute value squared, but then to get the absolute value by itself, we take the square root. So there we go. So let's just do a quick example, and then we'll move on to the last thing, which is how do you convert back and forth? So, well, what is trig form? We actually haven't even talked about that yet, huh? Okay, so example. If z is equal to 2 minus 5i, find the absolute value of z. Okay, so you guys try that on your own real quick. We'll put up the answer here. We'll see if we get the same thing. So you can pause the video now. Oops, sorry, I was trying to... All right, there you go. If you got the square root of 29, then you got it right. One thing I do want to point out, when you're putting the -5 in the formula and you're going to square it, make sure you put that in parentheses. You got to show that the negative and the 5 are both getting squared. If you don't, then it's wrong and you're going to lose points. And also, because that negative gets squared and becomes positive, this is a plus sign all the way throughout. It's one of the most common mistakes students will make. It's pretty straightforward, but that's a silly mistake people will make, is they'll have plus a minus and think that that just changes to a minus sign. So, all right. So now, what is trig form? Well, trig form of a complex number. Actually, I'll put all of that. Of a complex number. It comes from what we already know, thinking about back to our days of trigonometry. Again, I'll just put part of a complex plane here. Here's real, here's imaginary. I'm going to put a plus bi. Thinking about that triangle again that we can draw. The a and the b are really the x and the y coordinate if we think of it on a coordinate plane. And we know the x coordinate, in this case x is equal to a, but we also know that the x coordinate is r cosine theta, and the hypotenuse is going to be r. And then y is b, and we know that the y coordinate is r sine theta. So all we're going to do is replace the a and the b with r cosine theta and r sine theta, and boom, we got trig form. So trig form looks something like this. If I take a plus bi, a, like I said, was r cosine theta. B was r sine theta. That's essentially trig form. The formatting of it is a little different, but that's really all trig form is. One thing to notice is both terms have an r in it, so we typically write it with r factored out. And then, if I just have sine theta I, if I don't put the sine theta in parentheses, this actually means this, which is not what I want. I don't want the I included with the angle. So we're going to just move that I out in front. So it's going to look like this. Cosine theta plus I sine theta. And that is trig form of a complex number. And actually I should label here. Theta is the angle that we make with the x-axis. So, let's just put this a little more formally. Trigonometric form of a complex number. A plus bi is r cosine theta plus I sine theta. And just a little vocabulary. This guy right here, a plus bi, he is known as standard form. Whoops. Or sometimes you'll hear it called rectangular form. I actually can't remember what the book uses. I want to say standard, but I can't remember. But anyway, both of those are the same thing. And then likewise, I know the book calls this trig form because that's the name of the section. So trigonometric form, trig form. But another word for it is also polar form. So there we go. All right, so the last thing for this video then is converting back and forth between trig form and standard form. So let's do that. Oh, I'm at the bottom of the page. Okay. I'm going to go ahead and put it up there at the top. Okay, so with, like this works a lot like what we were doing before with our old stuff. We already said, like here's some formulas to keep in mind. We already said that A is r cosine theta and B is r sine theta. We also know that tangent of theta is B over A. And then the other thing to keep in mind is that r squared is equal to a squared plus b squared. And you can see that from the picture. It's just a right triangle, so it's Pythagorean Theorem. So those are the four formulas that are going to help us convert back and forth. Although, sometimes you don't need the formulas. So always try to stop and think first if you need them. So, let's just do a few examples, and then that'll be the end of this video. Okay, so converting from, let's do the easy one first. From trig form to, I'm going to bring this down so we can see the formulas, to standard form. Okay. So converting from trig form to standard form, it's not so bad. Let me move this out of the way. Sorry about that. Okay, so example. Let's just say that we had 7 cosine 30 degrees plus I sine 30 degrees. By the way, hopefully this looks a little familiar. Hopefully it kind of looks like trig form of a vector, the magnitude and direction form, because it's all closely related. That's why they're in the same chapter together. But anyway, we want to do this. It's really easy. Like if you want to just, pause the video again, try to think about how you're going to convert it to standard form, go ahead. But otherwise, we'll talk about it right now. Okay, so we have the formulas. Formulas are right here. All we need to do is find A and B, and we are given what R and theta are, so you just plug them in. Like it's really that easy. So, for instance, R is 7, theta is 30 degrees, and so A is R cosine theta, which is 7 cosine 30 degrees. Hopefully you still remember your values. The cosine of 30 degrees, I had to think about it for a second, is root 3 over 2. And so A is 7 root 3 over 2. B is r sine theta, which is 7 sine 30 degrees. The sine of 30 degrees is 1/2, so it's 7/2. So A is 7 root 3 over 2. B is 7 over 2, and then you just put it together. So the answer is 7 root 3 over 2 plus 7 over 2i. It's literally that easy. If the angle given was not one from our unit circle that we know, like let's say that was 59 degrees, you would still say 7 cosine 59 degrees. And then if you needed to get the decimal approximation, use your calculator. So that's pretty straightforward. Going the other way, you just have to be careful. When you're trying to find theta and R is straightforward. We're going to use this formula up here. R squared equals a squared plus b squared. But theta, you just have to be careful and make sure that you use the theta that's in the right quadrant. But other than that, it's not bad. So, for instance, oh, I should title this. So this is converting from standard form to trig form. So, for example, let's say that you have, I don't know, just shout out some numbers. Let me see if I get them. Okay, I think I hear a 3, and keep shouting them out. I heard a 7. I don't know if you guys said that. I'm just saying that. All right, let's say we have 3 minus 7i. So we need r and theta to go to trig form. R is easy. Let's just get the easy thing out of the way. R is the square root of a squared plus b squared, which in this case is the square root of 3 squared plus negative 7 squared. Look, r is the absolute value of a complex number. Keep that in mind for future videos. But anyway, 3 squared is 9, negative 7 squared is 49. Add them together, and r is the square root of 58, which won't simplify. I keep picking things that don't simplify, dang it. All right, so we got that. So now let's find theta. So with theta, remember tan theta is b over a. B is negative 7. Excuse me, a is 3. Oh, hang on. Sorry, wanted to grab my calculator. So theta is tan inverse of negative 7/3. Let's just double check. So I'm going to go ahead. First of all, I did degrees. We've been doing degrees a lot lately. With trig form, you can have degrees or radians. So I'm actually going to change my calculator. Well, no, I'll leave it for degrees for this. We'll do the next example in degrees, or in radians, I mean. But remember, whatever mode your calculator is in, that's the unit it's going to use to give you this. So I'm going to do tan inverse of negative 7/3, and I'm getting that theta is about negative 66.801 degrees. And remember that the range for tan inverse is between negative pi over 2 and pi over 2. It's always going to give you the answer in quadrants 1 and 4. But when you're in 4, it's going to go in the negative direction. Now, for purposes of this class, and it's really just to get you guys practicing, we're going to say that theta is between 0 and 2 pi, or 0 and 360 degrees. It doesn't always have to be, and then likewise r, we're going to keep r positive. Later on, we can get to negative r's in other classes. It just means you go the opposite direction. But anyway, we're not going to, r is always going to be positive. And I'll put it over here. R is positive, and theta is going to be within 1 rotation of a circle. So we're going to keep it there. So I need to add 360 to that to say 293.198 degrees. So I want to make sure I'm in the correct quadrant. If I think about where 3 minus 7i is, I go over positive 3 on the real, negative 7 on the imaginary. It is going to be down here in quadrant 4. 293 degrees is in quadrant 4. So this is all matching. So I'm good. So then I put it all together, and we could say that 3 minus 7i is r cosine theta plus I sine theta. Boom. Okay, so I'm just going to give you 2 more. Try these on your own. We'll come back. We'll see. We'll compare answers and that'll be the end. So the two that I want you guys to try, convert these. I want you to convert, let's say negative 5 plus 2i, and how about just negative 3i? Okay, so pause the video and go ahead and try those. All right, so here's the answer for the first one, and you can see that you have to be a little careful on this one. So keep in mind that this complex number is in quadrant 2, so that's going to be important when you're dealing with theta. R is straightforward. You just use a formula. It's Pythagorean Theorem. You're going to get the square root of 29. But when you do tan theta is 2 over negative 5, and so theta is tan inverse of negative 2/5. On the calculator, you're going to get this. And again, it has to do with the range for tan inverse. It's always going to give you answers in quadrants 1 or 4, not quadrant 2, which is what we want for this answer. So this answer is actually down here in quadrant 4. You got to add pi, or add 180 degrees to get it into quadrant 2. So that's the only trick. Otherwise, it's also pretty straightforward. And so there's your answer right there. All right. Last example, and I'm going to pause it in case you didn't get a chance to do that one yet, but we'll come back. All right, so here's this one. You could use the formulas if you want to, but this is what's going to happen. If they're ever quadrantal angles, or if it makes a 30, 60, 90 triangle or a 45, 45, 90 triangle, and you recognize them, you don't have to do the formulas. And in this case, it was much easier not to. If you think about where 3i is on the coordinate, or on the complex plane, the angle is going to be pi over 2 or 90 degrees, depending on which unit you want to use. And it's 3 units away from the origin, so r is 3. There it is. By the way, take a look at what would happen if you did use a formula. I don't know if any of you guys did. We know that tan theta is b over a, and so in this case, b is 3, but a is 0. But wait, you can't divide by 0. Tan theta is undefined. What? Well, if you remember your table, because you can't plug that in on the calculator. So now you're either going to have to think about the picture, or you can remember your table of values. But tangent is undefined when theta is 90 degrees or 270 degrees. And again, you got to use where the location of this to decide which one you're going to use, 90 or 270. So I just wanted to point that out. All right, so that's the end of the first video, and I'll see you in the next one. Bye.